Hello everyone, welcome to the subject IoT sensors and devices. Now we'll be looking into the unit of Introduction to Microcontrollers, and these are the topics that we'll be looking into: number system, logic gates, A to D converters, PWM, microprocessor, microcontroller, the differences, about the Arduino Uno architecture, and ESP8266. So first we'll be looking into what is a number system. When it comes to the number system, you should be aware that the decimal number system, that is base 10, this is the most commonly used number system that is used. You may be aware that through subjects that you studied earlier, there are other number systems that are available, which is to the base 2, which is called as binary number system, base 8, which is called as octal number system, and base 16, which we call it as the hexadecimal number system. Though these number systems are available in mathematics, the one that is commonly used in computing is the base 10. Now, when it comes to microprocessors, which if you study in later classes and you're working with assembly level language programs, that is where you will be talking much about the hexadecimal number system. But now we need to only focus on the decimal number system as we take in numbers only. Next, as I told you earlier, we have the decimal number system, we have the binary number system, the octal, and the hexadecimal. Decimal is nothing but 0 to 9, binary is 0 and 1, octal is 0 to 7, hexadecimal is 0 to 9 followed by A to F. So the most commonly one that is used by humans is the decimal number system, and it is also commonly used elsewhere. Next, we have the counting over here. As you can see, counting 0 to 15 we have over here because that's a common representation for hexadecimal number system. And when it comes to binary, we will be talking only with zeros and ones. In octal, we'll be talking up to 0 to 8 only. And when it comes to hexadecimal system, we'll be talking about 0 to F. Now, when it comes to the conversion among these number systems, it is easy to convert any of these number systems depending upon our requirement. Next, moving into the logic gates. There are several logic gates that are available. Why are they being used? They are being used to turn off and turn off a particular switch at a particular condition that is required. And they are the building blocks for computers from which logic gates we have flip-flops. From flip-flops we have the particular registers and the other logical circuits that are available. So when a particular condition is true, the logic gates turn on, otherwise it is turned off. So it is equivalent to a particular switch over here. They check whether the information is given is according to the certain rule or applied. The answer is of a binary condition, either true or false. And when you see the condition on, it is equivalent to condition 1. When you see the condition off, it is equivalent to condition 0. Next, logic gates, as you may see over here, you can see that the particular case in this scenario is when you give a 5 volt to the logic gate, it is equivalent to logic 1. That is what you need to remember. When you give 5, it doesn't mean that you're giving decimal number 5 or any other value over here. When you give 5, it is equivalent to logic 1, and when you give 0, it is equivalent to logic 0. That's the difference over here. And this is the example that will be that they have explained over here. When both conditions are equal, what is going to happen? When both conditions are false, what is going to happen? So these are the two cases that we are looking. And next, logic gates, different types are there, as you may be aware. So logic gates are different types. There are 7 logic gates, and they are explained with respect to their Boolean expression, logic diagram, and truth table. What is a Boolean expression? When you have an equation representation for a particular logic gate, we call it as a Boolean expression. When you're representing it in a diagrammatic format, it is called as a logic diagram. And the working of that particular logic gate in a table is called as a truth table. And inverter, as you are aware, you give the input and a complement of that is available at the output. You give 0, you get 1, you give 1, you get 0. So you have represented by this symbol over here, and this A complement, A is nothing but the input, complement of that input is nothing but the output over here. Similarly, when it comes to the simple AND gate over here, you can see that when both gates are 1, when both inputs are 1, you can see that the output is 1. Otherwise, the output is 0. It is equivalent to a multiplication operation. So that is where you get A into B. Next, coming into the OR gate, it is A plus B. That is when you add two values, 0 and 1, it is output 1. 1 and 0, it is output 1. And 1 and 1, it is output 1. 0 and 0, it is output 0. So this is just a simple addition operation over here, represented by this symbol. And you can see that this is your XOR gate over here. When two inputs are different, the output is 1. When both the inputs are same, the output is 0, as you can see over here. 1 and 1, 0 and 0. inputs are same, so the output is 0. So this is your particular XOR gate. And the next one is your NAND gate. Opposite of the AND gate is your NAND gate. You can go through that. And the next one, opposite of your OR gate, is your NOR gate. You can again go through that. Next one is your XNOR gate. The opposite of XOR gate is your XNOR gate over here. As we saw in XOR gate, when inputs are different, the output was 1. The opposite of that happens over here. When the inputs are different, the output is 0 over here. When the inputs are same, the output is 1 over here. Next, universal gates are the NAND gate and the NOR gate. Why do they call them universal gates? Because with these logic gates, you can implement any logic diagram which can be used to design any circuit. So next, moving into analog and digital signals. The basic thing that you need to understand first is what is the difference between analog and digital. Digital, as you can see in this particular diagram over here, there is an on and off. That's all. You can see the yellow light and you can see the black color darkness over here, which means that there is only two states. It is on and it is off. Only two states. But when it comes to analog, you can see that there is variation in the brightness of this yellow color, which means that it is not only 0 and 1, there are values in between. So this values in between is what you call as analog, whereas if there is only one set of value, that is what you call it as digital. So that is what we also call it as discrete. It is being broken into values. Next, what is the difference between a microprocessor and microcontroller? First, a microprocessor, it has its processing unit separate, whereas the RAM, your ROM, that is your random access memory, read-only memory, the timers required, and the I/O ports, all are external to the processor, and all of these are connected through external buses. So first you need to understand what is a bus. Wire is what that is used to carry data from one place to another. When you merge these wires together, it is what you call it as a bus. Buses can be depending upon the number of wires available. If there are 8 wires over here connected together, it is equivalent to an 8-bit bus. So that you'll be looking into detail a little further. So I hope you're able to understand processor is having its ALU, which is separate, but your data and your particular code needs to be stored somewhere, which is the memory. All of these are stored external to the processor, and that is what you call it as your RAM, ROM over here, and timer to do the specific functions, counting and all, and the IO devices. You need to connect sensors, actuators, and all these devices, and all these are connected through ports. These ports are available over here, and all of these are external. So this is what is the architecture of your processor. When it comes to a controller, all the devices that we spoke about, which was outside, is now inside the particular chip. So you have the processor along with the IO port, timer, RAM, and ROM, but they are connected not through external buses, they are connected through internal buses. So that's the major difference between a microcontroller and a microprocessor. So when it comes to microprocessor, area is large, whereas in microcontroller, as all of them come inside a particular chip, it is integrated and becomes small in size. So now we look into the differences between them. A few of them will brush up a little fast. Microprocessor is the heart of the computing system. So please understand that it's like your computing system computer, whereas microcontroller is the heart of the embedded system, which is the project that you're going to do, for example. And in a microprocessor, it's just only a processor. So memory, IO, and all these components have to be connected externally, as I told into the in the diagram. But here, everything is available internal in your microcontroller. Memory and IO has to be connected externally. Like the memory here, which we spoke of earlier, they have to be connected externally. So the circuit becomes very large over here. So everything is internal. So everything is small over here. You cannot use it in compact systems because the area consumed is large. You can use it in compact systems, microcontrollers. Cost is going to be high because it is processing large amounts of data, but here it is going to be small in size, so its processing capacity is going to be low. So similarly, its cost is also going to be low. And external components being available over there, the total power consumed is going to be high because everything is external. But here everything is internal, so it is going to be consuming less power. So for this, what is going to happen is you're going to require external batteries which are required for it. It is not ideal for batteries, but here it is ideal for batteries. You need a power supply over here, but here you require only batteries. Next one, most of the microprocessors do not have power saving features. Nowadays they have, but nominally power processors do not have this power saving features, but microcontrollers, they have these power saving features by default because it works on the battery mode. That is the main point. It mainly is used in personal computers, as we spoke of in the first point earlier. It is mainly used in washing machine, MP3 players, and other embedded systems. Microprocessor has a smaller number of registers. Microprocessor internal registers, as I told you earlier, logic gates, Logic gates combine together to form flip-flops. Flip-flops is used to store 1 bit of data, and flip-flops combined together form registers. Registers can be multiple flip-flops combined together. So this registers can be of 8-bit size, it can be of 16-bit size, or it can be of 32-bit size, and so on. These registers, which is available for processing the data inside a microprocessor, is comparatively less. But in a microcontroller, they have more number of these registers, which is used for programming and making the things easier to do. Microprocessor based on the von Neumann architecture, whereas microcontrollers are based on the Harvard architecture. These two architectures we'll be looking into a few slides later. You'll understand it. And this microprocessor, it's a CPU on a single chip. Whereas this particular microcontroller, it is having all the components integrated with the peripherals into this particular chip. And microprocessor, it has no RAM, it does not have a ROM, it does not have the IO units, neither the timers or other peripherals on the chip. Whereas in the microcontroller, everything is available on the chip. And it uses external buses to communicate to all three these devices to the microprocessor, and it has only the internal buses. Microprocessor based system can run at very high speed because the technology involved in high processing, but it can work only up to 200 megahertz. Your computer, as you may be aware, has a processor and it works in gigahertz speed. That is what you may be aware. And at 2.6 gigahertz processor, all these that you have heard of. So this speed is going to be in gigahertz range, whereas here it is just in 200 megahertz range. It's used for general purpose applications, whereas a microcontroller is specific in its applications. These particular controllers can be used only for specific applications which you are building. And when you are having a particular computer, you can install any software, you can use it for particular multi-purpose applications. So this differentiates that particular point. It's complex and expensive. As I told you earlier, it is comparatively less complex and less expensive. Examples of processors, you can see them: gaming machines, traffic light, military applications, and so on. But when it comes to microcontrollers, automobiles, it can be used in that, in DVD players, washing machines, cameras, and your keyboard controller. All these use these microcontrollers, which are lower cost. Next one, coming to the Arduino Uno architecture. Okay, so the different microcontrollers available over there, all of them vary depending upon these parameters only, four major parameters. First one is the width of the bus. So as I told you earlier, single wire is what we call as the data transmitting from one place to another. But when you combine these wires together, you want to transfer the bits in parallel. That is where you use multiple wires, and these wires combine together to form a bus. And this bus can be either 8-bit, 16-bit, or 32-bit. And that is what you'll be seeing over here. You have either 8-bit microcontroller, 16-bit microcontroller, or 32-bit microcontroller. The computers that you're using today, OS, it is 64-bit. This is just an example for you to understand how many bits are being processed at the same time. So this is 8-bit, 16-bit, and 32-bit over here. Next one, the memory devices can be classified based on either it is embedded memory microcontroller or it is going to be your external memory microcontroller. If you have your memory embedded into the microcontroller itself, there is no requirement for external memory. That is what you call as the embedded memory. It is embedded into the chip itself. The opposite of that is going to be the external memory, in which the program is going to be stored externally, whereas all other instructions are stored, where all the data, everything is stored internally over here. You have another external memory which is available, which is connected through this external interfacing bus. So this is an example for your particular what is external memory over here. The embedded memory, the example was 8051, whereas for your external memory, the example is your 8031 microcontroller. Now, classifying based upon the instruction set that is available. You may be aware that normally we use high-level languages, which could be C, Java, Pascal, whatever they may be. These instructions are easy for us, but it is complex for the particular computer. Why is it complex? Because we combine instructions together. We say that C is equal to A plus B for as an example, which is combining not only addition of two operations, it is also getting the data of A and B first. So you're moving the data of A and B, adding the data of A and B, and you're moving the data into C. So you're combining all operators together just by giving the value C is equal to A plus B in a simple C instruction. Whereas if you want to do it in an instruction level, if you want to do it in a microcontroller understandable level, first you have to do the data transfer operation. A, this is equal to 5, B is equal to some value 10. Then what you have to do in your next instruction, you have to give the addition of these two numbers. Then in your next instruction, you have to give that the output of this should be moved to this particular variable over here. So all of these are given separately when it comes to a reduced instruction set, which is the next type. But this complex instruction set, for us it is easy, but for the machine it is difficult. RISC, as I told you, reduced instruction set is reduced number of instructions over here, which is for us it is difficult. We have to write more number of lines in the program, but for the computing facility it is easy for it to debug it. Next one is, as I told you earlier, Harvard architecture and von Neumann architecture. It was now found at the Harvard University. The processing unit is now separated by the two memories. There are two main memories available. One is called as the instruction memory and the other one is called as the data memory. Instruction is used to store your program and your data memory is to store the data that is coming from that particular program. Either it could be from sensors or whatever timing, whatever it may be. So if you have separate buses for these two, that is what you call it as a Harvard architecture. Separate bus for carrying the data, that is carrying your program to the processing unit. Separate bus for carrying the data to your particular processing unit. So as I told you earlier, C is equal to A plus B. What is your instruction over here? C is equal to A plus B. What should happen over here? A data should be moved to control unit, B data should be moved to control unit, add these two values and then you have to put the data into C register. So A and B moving this side, C data moving outside to the data memory, whereas your instruction is separate over here. So if you have separate data buses, that is what you call it as a Harvard architecture. But when it comes to your particular von Neumann architecture, you have a single bus only available over here. You are having the memory which is available inside the processor. There is only one single bus available over here. So with this single bus, what you have to do, you have to move the instructions, then followed by that, you have to move the particular data. So what is the Harvard architecture? First, you can move the instructions simultaneously, you can move the data. Both could take place at the same time. But here, one after the other only you can take care of them. So that is a von Neumann architecture. Two different architecture having their advantages. What is the advantage of the Harvard architecture over here? You are saving time. You can move the data separately. But the drawback is it is taking a lot of space. You have separate buses over here, which is one used for instruction, one used for particular data. But when it comes to this von Neumann architecture, area is less because it is just using a single set of buses rather than two sets of buses over here. The area occupied over here is less. But when it comes to your particular processing speed, it is going to be slow because first you will have to move the instruction, then followed by that you will have to move the data. So it is going to take a lot of time. So this type of architecture is good for controllers, and whereas your Harvard architecture is the one that is good for processors because speed matters when it comes to processors. Then there are different other processors, controllers available in the market. Now we'll be looking into the Arduino Uno architecture. Arduino board was found by Ivera Interaction Design. You can go through these particular slides in detail. I will just brush up on the details that are available here. It is good for 3D printing application, wearable and embedded surroundings, and you can build applications depending on your need. It is working on Windows, iOS and all these operating systems, and you can do any projects depending upon your requirement using fire sensors, GSM modules which is fine to send messages or calls, GPS module which is used to find your location, your whether there or not, using presence detectors, obstacles. All these can be done using these particular things. So we'll be looking into this particular Arduino Uno based on its capabilities that it can do. Now coming to this Arduino Uno R3 architecture, we'll be looking into the important parameters that we need to do. First is your USB plug. This is where you're going to connect it through your particular laptop. You might have seen this in the Arduino board. Through this only you can download your particular program, and it can also act as your particular power supply. Next one, beyond this power supply, if you have downloaded your program into the Arduino, you can just connect it to an external power supply and make this microcontroller work. So for that, you need to have an adapter which is going to be from 9 volt to 12 volt over here. Now, this Arduino works with the 5 volt. So for that, you need the corresponding 5 volt regulator over here. So this is your 5 volt regulator which converts the higher voltage into the 5 volt. And this 5 volt can be taken from this particular pin of your particular Arduino, which can be given to sensors or other devices. Other than 5 volt, you also have another regulator which can be used to convert it to 3.3 volt, which is used by devices. So So you have a 3.3 volt, you have a 5.5 volt. Now you have, when the connection is getting over is only when you have ground pins. So there are two ground pins over here and there is one ground pin over here. So there are another ground pins over here. You can give input voltages through this particular voltage in, and beyond that you have this analog reference which is going to be used in comparator based operations. Now the important parameter is you have digital pins, you have analog pins over here. How many digital pins do I have? 0 to 13, which is 14 digital pins over here. In that, two pins are used over here for protocols which are using serial communication like I2C protocol and so on. So you have TX, RX, and which is used for serial communication. So it is a part of this particular digital pin. You have the reset button. Normally the reset button would be over here in some devices, and mainly you have this Atmega 328 controller. The common mistake that many people do is they consider this Arduino as a microcontroller. Please remember, it is wrong. Arduino is just the name of the board. This Arduino is just the name of the board over here, Arduino Uno. Uno is the name of this board, Arduino is the name of the company, whereas the controller that is used inside is Atmega 328 controller. And this is your IC over here. And when I'm able to get digital inputs, I can also take out digital outputs. That is the purpose of this digital pins over here. Next, you have this particular analog in. This analog in over here means I can give an analog inputs to my particular controller. How many analog inputs can I give? A0 to A5, which means 6. You can see that it is specified as analog in. I cannot give analog out over here. That is a major drawback. And that is where you have this PWM. I can specify analog outputs to a certain range, and that is where I have this PWM. Every pin over here that is represented by this wave symbol is called as the PWM. Pin number 3, 5, 6, 9, 10, 11. So we'll be looking into this PWM in the later slides. You can just go remember that. So we have 6 analog pins, we have 6 PWM pins, which is again a digital pin, and those digital pins are totally 14 in number. So these are the main components of your Arduino Uno. And you can make major projects out of these, and that is what these points over here are explaining. Next one, you'll be seeing that it has two memories. One is for storing the code, which is called as your flash program memory, and the other one is for storing the data, which is called as the data memory. So the flash memory, which is used for storing the code, is 32 kilobits in size in Atmega, whereas in that for 0.5 KB is used for the bootloader, which is nothing but the equivalent of your operating system. So if a computer, if you're talking about, we call it as operating system. Here we call it as the bootloader. So 32 kilobytes of memory in the flash is used for storing your program. Then you have 2 kilobytes of SRAM and 1 kilobyte of EEPROM to store the particular data. This is what is available. This is your architecture. As I told you, you have the supply pins, everything over here. You have the analog pins available over here. You have the reset button available here. You have the digital PWM pins along with the ground, everything over here. And you have your cable, interfacing cable, which is the USB connector, which can be used to connect to the PC, which is here. This is your particular regulator, which is available over here, and power switch, and this is your particular power adapter that is available over here. So power, we have VN 3.5, 5 volt. As I told you earlier, these are the power supplying options, and you have the particular ground. You have a reset pin, which is used to reset the microcontroller. Other than the reset button, you can connect it to this particular reset pin. You have 6 analog pins, A0 to A5, which is available. Then you have your input output pins, digital pins, which are 13 in number, which is both input and output. Then you have the serial communication, which can be used TX and RX, and you will be using them in applications in future. Then you have interrupts pin. Now you want to stop a particular process. It's like an alarm. After some time, do this particular interrupt and so on. Or someone is saying that you have to do this particular task when you press the keyboard. So these are called as interrupts. Moving the mouse cursor, pressing the button of a keyboard. All these are interrupts to a particular computer. Similarly, you have these two interrupts which can take care of those operations. Then you have the PWM, which I told you, there these pins which are available over here. Then you have your SPI, which is serial peripheral interface. You have these pins over here, which is master out, serial in, master in, serial out. If you want to connect two microcontrollers together, one has to act as a master, another as a slave. So which is going to be the master, which is going to be the slave? All of these are taken care by this particular SPI. These are advanced level. In future videos, we will be looking into this. Then you have an inbuilt LED to check whether your blinking program is the basic one that we normally do here to check whether your controller is working fine. Then you have the two-wire communication protocol, which is TWA, which uses SDA and ACL. So these are the particular thing SCL over here, which is nothing but your clock, and SDA is for the data, serial clock. This is the most commonly used protocol which is used in communication. We call that as the I2C protocol, which we'll be using in most sensors. And next one is the reference voltage to your input voltage, which is given over here. And to give you an outline, in your architecture, we saw that it has a flash memory and it has a particular SRAM. So all these memories are available over here in this particular EEPROM and your SRAM. Three memories. This is for storing the instruction. This is for storing the data over here. So from the instruction, you will put it into a register, which is going to be decoded. And when this register is having the instruction, next step is to decode that instruction, to understand what that instruction is going to do. If it is A plus B, it is understood that I need to add two data. So machine needs to understand it by decoding it, and accordingly the control lines are given stating that, okay, get the value of A from here, get the value of B from here. So the control lines are coming over here. What is a program counter? It is going to say that what is the next address of the next instruction that is going to be executed. So when one instruction is getting decoded, the next instruction is now moved to the instruction register. All of these happen one after the other. Status and control to make sure everything is going fine over here. As I told you, in microcontrollers, they have more number of registers. We saw that as one of the points. Microprocessors have less registers, whereas microcontrollers have more number of registers. There are approximately 32 8-bit registers that are available to do applications. All of these data are given to the arithmetic and logical unit to do the particular operation. And you have that interrupt unit, SPA unit, which I spoke about earlier, the timer and the analog comparator to do the specific operations depending on the timing. And these IO modules are the ones which are used to connect the sensor and the particular actuator, that is the output device, to your particular controller. Next, the UNO architecture, already we saw them. They have all these pins available here. So these are the reference data for that. For when it comes to the digital pins, you should be aware that it will give you only a value of maximum 0 to 1023. These are the values only you can get. Beyond 1024, 1025, all these values are not available because it is having a 10-bit resolution. Please understand that your digital pins has a 10-bit resolution only. If it 10, and how is 10 related to 1023? You can see that 2 power 10. 2 power 10 is equal to 1024, which means it is 1 to 1024. Here it is 0 to 1023. So if you have a sensor connected to your particular device, probably in the later video I will tell you, if you have a sensor connected, the minimum value that you can obtain from that sensor is 0, whereas the maximum value that you can obtain is 1023, not more than that, because of this 10-bit resolution. Then you have that SDA, SCL, all these pins are available for that, and the reset pin. So this particular controller, we saw that on the outline, and we have the particular memory which is available over here to store the particular data, interrupt unit to check for interrupts. You have the serial peripheral interface, as I told you earlier, SPI, which is used to take the data from camera, display, SD cards and all. So that is where you'll be using this SPI. Watchdog timer is used to check whether your microcontroller is malfunctioning or not. If it is malfunctioning, it will reset your entire controller and come to a known state. Okay. If your microcontroller goes into an unknown state that it is not able to come out of, it is going into an infinite loop or whatever, then this watchdog timer comes into the picture and resets your microcontroller and comes into a known state. Then you have the analog comparator to compare the values over there, status and control to check the particular value. ALU unit is for doing the arithmetic and logical operations, and the different IO pins are used for connecting the sensors, actuators, and other such ICs which are available. Next one, we need to look into ADC. ADC is nothing but analog to digital converter. We have 6 analog pins which are available. Data is available analog in the outside world, but your microcontroller only understands digital data. So how am I going to convert this analog, which is the real world data, into the machine understandable digital data that is taken care by this analog to digital converter? And that is where you see this analog to digital, analog input, whereas your output is going to be digital or binary in nature. And for that you have the particular power supply which is connected over there. The commonly used analog to digital converter is ADC 0808. So that is your analog to digital converter over here. This is the IC. You just need to know what is happening over there. So we'll be skipping this particular part. So we'll be moving into the features. which is it is an 8 channel. This 80 ADC 0808 is an 8-bit ADC. Earlier we saw that we had a 10-bit resolution with this particular what do you say digital pins. Similarly, the analog pins are also of the 10-bit resolution. This ADC 0808 is having an 8-bit resolution over here. Next one, when you come into the particular DAC, it is going to do the opposite. For example, your microcontroller is processing all the binary data. It needs to convert that into an analog data when it needs to reach the outside world. For example, you want to use a particular motor which is going to vary in speed and so on. That is where you need to convert this binary value into a mechanical value over here. So electrical to mechanical. So that is where it comes into this process of digital to analog conversion. It has its applications, and that is where, as I told you, PWM comes into picture. So we'll be looking into the PWM shortly. And next one, this is the IC DAC 0808. It was ADC 0808 for analog to digital. Here it is DAC 0808, which is going to be digital to analog converter. And next one, there are some special features of them, and you can go through them. Next one, mainly conversion of audio. So if you want to have, you have your binary data of an audio file, you want to make it audible to others, you need to convert it to an analog value. That is where the DAC comes into picture, and it is used for other electrical measurements and so on. So where will you use an ADC and DAC combined together? So for example, if you have a mic and you are having your controller over here, which is like your computer, and you want to put it on a speaker. This is where you have the combination of ADC and this particular DAC. So you have an analog data, which is the input given to the mic, which is converted into digital data for processing. Then you need to amplify it accordingly, and that amplified signal needs to be converted back into an analog signal which is being heard by us in the speaker. So you have an analog to digital converter followed by a digital analog converter. And the best example for that is what I am telling you till now. You are speaking over the mic, which is analog data. That analog data needs to be converted into digital data for signal processing over here. This digital data cannot be used directly and heard by us in speakers. You need to convert them into an analog signal. Well, that is where the DAC comes into picture. So this is the combination of the combo of ADC DAC. Okay. So next, as I was telling you, PWM. What do you mean by PWM? Pulse width modulation. So I am varying the width of my particular pulse signal. Normally, every pulse signal will be of equal duration. It will be equal time on, equal time off, equal time on, equal time off. So this is what we call as a pulse, or we also call it as a square. Why do we call it as a square? Is because it is having equal durations of on and off time. Now, what is the purpose of this PWM is, I need to vary the particular duration over here. Why do I need to vary the duration? For example, I have an LED or I have a motor with me, DC motor. I need to vary the brightness of this LED. Normal LED experiments that you do is you either turn it on or you turn it off. With my digital pins, that is the only option that I can do. Digital pins can either turn it on or turn it off. Or if I have a motor, I can turn on the motor or turn off the motor only. But I need to vary the brightness of this LED, or I want to vary the speed of this particular motor that is rotating. That is where I need to vary the on time and off time of this particular signal. So totally you can see that it is 50% on and 50% off. So for a square wave, the duty cycle, this is what we call it as the duty cycle. The duty cycle is 50%. 50% represents only the on time, not the off time. So what I'm going to do is I need to vary the another on time of this particular signal. When I vary the on time, for example, if I keep the on time to be 10%, my default, you can understand the off time is going to be 100 minus 10, which is 90%. So on time is 10, off time is going to be 90. So the duty cycle of this particular signal is going to be 10%. It is not 90%, 10%. So which means that 10% I'm getting the supply. Remaining 90% I'm not going to get the power supply. So 10% I'm getting the power supply means my LED brightness is going to be very low. You may be aware. Now I put it in the opposite way. For an opposite way, I am putting it 90% on and 10% off. What is going to happen? 90% of the time the power supply is on and 10% only it is off, which means that I'm going to get maximum brightness of my LED. So this is where by varying the on time of my particular signal, I can vary the brightness of my LED or I can vary the particular speed of my particular motor. So this has a variation of 5 volt or 3.3 volts. So 0 to 5 volt, or 0 to 3.3 volt, the values that I was talking about, you're going to vary that with the percentage of your on and off time over here. And that is what you call it as PWM. And as I told you, digital pins, they normally work with a range of 0 to 1023, whereas your PWM pins, they work with a range of 0 to 255 only, which means it is having a resolution of only 8 bits. 2 power 8 is nothing but 256. So please remember, digital pins have a range of 0 to 1023, which is because it is having a 10-bit resolution, 2 power 10, whereas your PWM has a resolution of only 0 to 255. So which means that if you give 300 in your PWM pin, it will consider it only as 255, which is because the PWM range is having a maximum value of 255. So if you want to have maximum brightness, you have two options. 0 to 55. Probably I hope you will only choose 255 because it is having a 100% duty cycle. 100% the time is on over here. It is not having an off time. If you have a particular value 0, it means your entire signal is 0. It is not going to the on state. No supply is given, which means it is off the entire time. So you can understand by this particular waveform over here, you can see that the black color line over here is specifying the particular signal. If it is entirely 0, you can say that it is 0% duty cycle because the on time is 0, whereas the the off time is 0% of the entire signal. So it is equivalent to a DC signal. This is an AC signal which is having positive negative. This is an AC signal positive negative. This is an AC signal which is having a positive and a negative. Again, this is a DC signal because it has only a positive and it is entirely 5 volt. Here it is entirely 0 volt. So which means in this case my LED is off, which is off over here. But in this case my LED is going to be on and having the maximum brightness because 5 volt is entirely provided the entire time. Now when it comes to this particular 0 state, if I keeping it on for 25%, you may be able to understand that my brightness is increasing further. From off, it is increasing. When I increase my duty cycle to 50%, my brightness further increases. When I increase the on time to 75%, my brightness further increases, but it has not reached the maximum. When I increase this 75% to 100% without having any off state, this is where it becomes a DC signal and my brightness is at its maximum. I hope you're able to understand that. So when it is equivalent to 100%, I told you the value is equivalent to 255. When the value is 0, it is equivalent to 0% duty cycle. When it is 50%, it is half of this particular 255, which is nothing but 127. So when you give 127 in your microcontroller, in your program, it will understand it to be 50%. This conversion is what I wanted you to understand. And the application I have told you earlier, why is it going to be used? So this PWM is available in your Arduino itself. When you go into the Arduino software, you can go into Sketch, Example, Analog. You'll be having that option of this particular program, PWM. You can work on that. And the last topic over here that you're going to see is ESP8266. It is a node MCU. Node microcontroller. In this node microcontroller module over here, you are having this ESP8266 available, and it is an inexpensive system on chip. So it is using open source software, as in the case of Arduino. This ESP8266 can be used using your Arduino itself. All these you are aware of. It has its own CPU, it has its own RAM, it has its own networking, it has its own operating system. All are the advantages. Your Arduino did not have this option of networking and its own OS. That was a major drawback. Now, if you want to build an IoT based application with just an Arduino, you cannot do it. With an Arduino, with it having an Ethernet port, like the Arduino Leonardo, which can be used over there, if you have an Ethernet port, then it's fine. Or if you have a separate Wi-Fi module integrated to that, then it's fine. But if you want everything to be available on a single chip, a single board, that is where you're going to have this option of having the ESP8266, which is nothing but your node MCU. Who found this ESP8266? It was by Espressif. That will be coming into ESP8266 is the name of this particular controller that is used over here. Node MCU is the name of the board. It is low power because it is working only with 3.3 volt and it is having a Wi-Fi processor there. 7 external components are available over here. It works in the range of -42 plus 125 and it has an 8 MB flash embedded memory over here which is available. And that and the memory name is 8285. That's the name of the particular memory. It works with the micro USB. Micro USB port is what is works on, and it has its own regulator, and along with that it has its own reset and flash button over here. It has its inbuilt LED which is available. This is its controller, and this is the Wi-Fi antenna. This Wi-Fi antenna is available on the PCB itself. This zigzag symbol over here is actually the antenna which is used for wireless transmission of the data through that Wi-Fi module. So as I told you earlier, it has micro USB to power it up using that particular USB port. It has 3.3 volt power supply which can be given. It has a ground, or you can give a particular power supply externally through the particular VIN pin. Either through the power supply port over here or through the VIN pin, you can give the external power supply. It has an enable and reset pin over here. Then it has one analog pin. Arduino Uno had 6 analog pins, but here it has only one analog pin, which is called as A0, which works in the range 0 to 3.3. Then it has 16 GPIO pins, that is your digital pins over there, GPIO 1 to GPIO 16. GP stands for general purpose, IO stands for input output. So it is both input and output over here. GPIO pins, which is connected to this node MCU. It has the ST serial data, its command and its clock signal, which is used for serial peripheral interface. It has the UART, which we were talking about, the TX and RX pins. So it has two UART pins available here. These are all protocols which we'll be looking into further videos later. And as I told you earlier, I2C, the most common one used in sensors. I2C pin uses the one that we saw earlier, SCL and the SDA. So these are the two pins that are used over here. And next one, as you can see, these are the pins available. You have one UART, one SPA, one I2C, flash memory is 4 MB, SRAM is 64 KB, clock speed is 80 megahertz, and it is USB TTL based. It has this particular CP2102 type of. This driver is the one that you need to install when you are using this particular hardware. It has its own PCB antenna, which I showed you earlier, and it is small size module which can fit into any of your IoT projects. Input voltage can be of 7 to 12 volts as we saw earlier. It operates in the voltage of 3.3 volts. So it has its corresponding regulator over here, and it is having 16 digital IO pins and one analog input pin. So I hope you're able to understand this particular topics of microcontrollers, in which we saw from the beginning with respect to number systems. We saw about the basics of logic gates. We saw the difference between microprocessor and a microcontroller. Then we saw what is an analog and what is a digital signal. Then we saw what is the difference between what you say ADC and the particular concept of DAC. Then we saw what is the concept of Arduino. And in specific, we saw what is the Adeno Uno there, and later we saw what is the concept of PWM, which is very important, and later finally we saw what is that ESP8266, which is nothing but your node MCU controller. So I hope you understood this video. Thank you so much for watching. Bye.